Okay, let's take a look at how we find arc length. Now, I'm asked to find the arc length of this function y equals x to the 3/2 minus 1 on the domain 0 to 4. So, first I'm going to do is write out my formula. We got that from part 1. If you go back and look at it, we showed you how do we find that. It's just the antiderivative from a to b of the square root of 1 plus our derivative squared, dx. So, if I graph this function here, we know what this looks like. It's x to the 3/2. It's a square root function starting at -1, so it's going to be kind of curvy like this. The 3 power doesn't really matter because x can't be negative anyway, so that's our basic shape. We want to find the arc length from 0 all the way to 4. So in other words, if I were to kind of sketch it out, that's the arc length we are looking for here, s. Now the first thing our formula tells me we need to find is the derivative. So if I take the derivative, y prime, we get 3/2 x to the 1/2. And I just plug that into my formula here. S equals from 0 to 4, the square root of 1 plus 3/2 x to the 1/2 squared. Don't forget the dx. And I simplify this. S equals from 0 to 4. We get 1 plus 9/4 x dx. Now, we are going to solve this by hand. So, what do we need? U substitution. We let u equals 1 plus 9 over 4x. So, du is just 9 over 4 dx, and dx, can I write that as 4 over 9 du. So, we should be getting pretty good at u substitution. I can now rewrite this as s equals, factor out the 4 over 9, and this just becomes u to the 1/2 du. I am going to change my domain, in this case right here. And if I change my domain, remember if x is 0, u is 1, so it's going to go from 1. When x was 4, to get u, I plug it in, I get 10. I change my domain, keep in terms of u. Taking the antiderivative, we get 4 over 9 u to the 3/2 times 2/3. And we're going to integrate that from 1 to 10. And if we just use the FTC here, the arc length, if I bring out the 2/3, I'm going to get 8 over 27. Plug in 10, I get 10 to the 3/2 minus, plug in the 1, I get 1. And I don't know what that is, so I'm just going to go ahead and leave it. And there's our arc length right there. Very easy to do these. So let's take a look at a slightly harder one. Not harder in terms of the problem, but the algebra itself. Number 2 here, y equals 3 x to the 2/3 minus 10 on the domain 8 to 27. This is a little trickier one right here, so if we want to take a look at this one, it'll be very helpful for you. Alright, wait till it focuses. Focus, focus. It's not that hard. Okay. Gosh. There. Come on. There we go. So again, I'm going to try to sketch this out. This time it's a cubic graph at minus 10. So we know what a cubic graph looks like. It looks like our Superman function, I like to call it. So we know on the positive side it's going to look kind of like this. Well, the square is telling me instead of going down, it's going to go up. So it kind of looks like the birds I used to draw in elementary school. There we go. And we're going to integrate this from 8 to 27. So in other words, now I'm looking for this, I'm looking 27 there. I'm looking for this arc length right there. My formula says I need the derivative, so I take my derivative, y prime, and that's going to give me 2x to the negative 1/3, and if or 2 over x to the 1/3, and I plug it into my formula. From 8 to 27, we get the square root of 1 plus, and if I square that, 2 over x to the 1/3 squared, don't forget the dx, and I'm going to square this. 8 over 27, I get the square root of, this becomes 1 plus 4 over x to the 2/3 dx. Now, we're going to do this one by hand, and things are about to get really ugly. I'm going to use a common denominator here. And if I write this as a common denominator, it's going to be 2/3. Give myself a little bit of space. My common denominator, this becomes an x to the 2/3 plus 4 over x to the 2/3 dx. Now, if I notice on bottom, the bottom's an even power. So I can take the bottom out of the square root. And that's going to give us, and this is, like I said, not going to be a pretty one, so bear with me, 8 to 27 of the square root on top stays the same, x to the 2/3 plus 4, but the bottom is just x to the 1/3 if I take the square root of it. And now what's really kind of neat is I can use u substitution. I'm going to let u equal x to the 2/3 plus 4. Now, people always think, Mr. Werner, how would you know to do this? Somebody showed me, and I'm showing you, so now then you can go ahead and know it as well. Some people just think like this, and we're proud of them. So, because now if I take the derivative, this becomes 2/3 x to the negative 1/3 dx. So dx equals 3/2 x to the 1/3 du. And if I plug that in now, 8 to 27, matter of fact, I'm not even going to plug those in yet. Remember, I'm using u substitution here, so I'm just going to leave those alone. I get u to the 1/2 on top over x to the 1/3 times 3/2 x to the 1/3 du. The x to the 1/3s cancel. Kind of cool. Factoring out the 3/2, u to the 1/2 du, and now I'll change my domain. When x is 8, u is also 8. You can check that. When x is 27, 9, that becomes 3 squared 9. U is 13, so we can go from 8 to 13 now. And we can integrate the rest here pretty easily. So I would get, what's that? 3/2 times, from 8 to 13, u to the 3/2 times 2/3. Oh, kind of nice. Those are all going to cancel out. So my final answer becomes just u from 8 to 13 of u to the 3/2. Applying our FTC, we get 13 to the 3/2 minus 8 to the 3/2. And there's the area under your curve here. And why does it keep going? Fun focus on my final answer. So, and there we go. Now, very hard to do, okay? So take some time. Now, on our last example, we're going to take a look at a problem. What happens if it doesn't work out so nicely for us? So let's take a look at number 3 here. And I'll focus in here real quickly here. Come on. Definitely fast forward through those. So, oh gosh, darn it. Come on. Focus. Now, let me write it out. Maybe they'll help it. Y equals, let me write it out first, 4 minus x squared on negative 1 to 3. There we go. Now, you might be saying, Mr. Werner, why would you use a calculator on this simple one? Well, let's try it. If I graph it, it's just a simple parabola from here to here. And we want to go from negative 1 to 3. So I'm looking for this arc length here. I'm looking for that arc length. So my rule says, what do we need? The derivative. So I take the derivative, y prime equals negative 2x. Plug it into the formula. Negative 1 to 3. The square root of 1 plus negative 2x squared dx. Simplifying this, negative 1 to 3, and I get 1 plus 4x squared dx. Now take a look. On the other two cases, because of square root, we could use u substitution. But here, u substitution will fail, because our du is 8x. Now the 8's okay, but the x won't cancel with anything. So u substitution fails. Matter of fact, there are quite a few functions that we cannot find the exact arc length. For example, an ellipse. An ellipse, even though it's a simple graph, we cannot get the exact arc length around it. We have to use Taylor series to get the exact values for these. Or another type of series or a sequence to get the exact values. And those are only approximations. So we're going to use the calculator for this one. Now you might be saying, Mr. Warner, if we couldn't get the answer, how could the calculator do it? Well, the calculator always only approximates anyways. The calculator is programmed to use only a bunch of types of series anyway. So we'll talk more about that later on. So I'm going to use my calculator, Math 4-2. And this is going to go from -1 all the way to 3. And I'm just going to type it in, square root of 1 plus 4x squared dx. I hit enter, and I get this, 11.226. By the way, just units. By the way, if you're looking at just units, not unit squared or cubed, something like that, just units. Well, anyways, that's some practice on these, okay? So take a look at a few more examples if you like on your homework and everything. I'll see you guys later. Bye-bye.